Good morning. This is Ms. Billerbeck, and we are going to talk about 10.5 compressions and stretches of functions. So if this pink is my parent function right here, then a stretch, a vertical stretch, would make the parabola stretch toward this y-axis. However, if it's a horizontal compression, that's in reference to this axis, the x-axis. So as we can see, this blue and this green parabola are stretching farther away from this x-axis than the pink parabola here, which is the parent parabola. So this is basically being pushed away from the x-axis, which is the compression. So we're compressing it away, versus if it's in relative to the y-axis, it's being pushed toward the y-axis, which makes it a stretch. Now, when we look at this side, we see, well, the blue is now being pushed away from the y-axis, and the green is being pushed away from the y-axis. So this is a vertical compression. However, it's being pushed toward the x-axis, which in reference to the x-axis, this is a horizontal stretch. Now, when we look at the formula, this is how we can tell the difference between a vertical or horizontal stretch or compression. It's where K is. So if K is on the outside of the function and multiplying the whole function, it's a vertical stretch or a vertical compression. If K is in reference inside the grouping symbol and with the X, and not the whole function, but just the X, then it's in reference to the X-axis. So that's what makes it a horizontal compression or a horizontal stretch. So let's do a few examples. So let's write a function that is a reflection across the x-axis. So all we have to do that is we can write g of x equals negative x. Now it's a reflection across the x-axis. So if I had the original function here, yx, and I drew the y equals x line, that's this line, whoops, that's that line right there. Okay, by making it y equals negative x, now I've just gone and drawn it this way. So we see in reference to the x-axis, it's reflected about the x-axis. Okay, so when we do this one, we just do the same thing. So we just put a negative in front of the whole function, and that reflects it down below. So in this case, if I had my square root of x, which is going to look something like that, as soon as I put a negative on it, then the square root of x now looks like that. So it reflects across the x-axis. All right, so if I do this with this one as well, I have negative, and then I just do x minus 2 squared. So again, if I have this one here and do x minus 2, that's just a shift to the right too. So it's going to come down like that, be a parabola. So I have my y-axis and my x-axis. And then down below, the reflection would just look like this. So there we have it. That's all a reflection is it's just a negative in front of the function. right. So let's write a function with a graph that is a vertical stretch of the graph f of x away from the x-axis. So that's important. It's away from the x-axis and it's more toward the y-axis. So if we want to write this as a vertical stretch, then anything that's greater than 1 as my k. So k has to be greater than 1 for this to happen. So I should write that right here. K is greater than 1 if we're looking at f of x or gk times, there we go, g of x equals k times f of x. So that's what we're looking at. All right, so then this just means that I'm just going to put in maybe a 5x. Okay, so that since f of x is x, I can just write 5x, and that's a vertical stretch. In this case, I would write, let's go with 7 times the cube root of x. I could also write something like this, h of x equals negative 3 cube root of x, because the negative 3, as we saw, even if it is a reflection right here, it's still a stretch, a vertical stretch when it moves away from the x-axis. All right, so for this one, all I have to do is put a, the a, remember a? It's usually right in front of there. A is going to be greater than 1. So I can put in a 4x minus 2 squared, and that's going to stretch it up. So it'll be a little closer. So let's do a quick graph of what we just did. So if I have my original here, so if I had the original one there, and then let's look at this in blue this time. So 5x just means it's going to move more like this. So it's getting closer to the y-axis. All right, this one's a little bit harder to do, but let's do this. So we come around here, we have the cube root, so we're coming in like this, but we're stretching it toward the y-axis, so it's way up here like this. And that's what the 7x does. And then if we had this one, it would just, this would be reflected over this x-axis. So I'm only going to graph this one right here. Okay, so this final one, if we have our original, we have this still coming down like this. And we have our y and our x. Now this is shifted, so it's not exactly going to reference to that, but if we have the axis of symmetry, it's going to stretch upward toward the axis of symmetry. So if it's 4 times, then it's going to look like this. Okay. So there you go. The axis of symmetry is acting like that y-axis that got shifted by 2. So now let's write a function that is a vertical compression of the graph f of x toward the x-axis. So if we look at this one, this will actually be the absolute value of k is greater than 1 for a vertical stretch. So that means it could be -1 or -2, -3, etc. or it could be positive 2 and positive 3. So when we look at this one, our K is going to be, we have -1 is less than K. But K can't be 0. So we're going to have to put a restriction on that at 0. And then we have 0 is less than K is less than 1. So that's what our K is going to be. So we can't have K equal 0 because then it's just the x-axis. Okay, so let's look at what this looks like as a vertical compression. So if we have g of x equals, let's say 1/4 of the 4th root of x, okay, so that's what that would look like. And then this one would be g of x. And remember, we can go negative, but it just has to be in this area here. We could say -2/5 the absolute value of x. And then this one, we have g of x equals, let's just make it 1/3 x minus 2 squared. So it's just going to be pulling it down a bit. So if we were to graph a 4th root, okay, we have y here, we have x here. So at 0, the 4th root's still 0. Our next one would be 1, so 0, 1. And then the next one to be 2 would be 16. So that's way out here. So the 4th root's a really flat curve like that. So the 4th root of 16 is 2. Because 2 times 2 times 2 times 2 is 16. So it takes 4 2s to be 16. 4 2s multiplying. So now let's look at what 1/4 would look like. Well, that's going to flatten it out even more. So it would look like that. Okay, so that's the compression. So then if we look at the absolute value, so this absolute value is going to start, our original one would start like this. We have our y and our x. And then at 2/5, it's going to be in here. It'll be very flat and it's going to be reflected because of the negative, but it'll have a very flat slope of rising 2 running 5, or rising 2 running 5. There you go. So, well, rising -2 running -5, or rising -2 running +5. Okay, so that's for that one. And now let's look at this. So we have y, we have x. We've got our shifted parabola. Okay, and then we are going to make it, I call it the wilting rose. It's going to wilt more toward the x-axis. And this is what a vertical compression looks like. So it compresses closer to the x-axis in all these cases. All right, so y is g of x equals 0.2x plus 2, a horizontal stretch of f of x equals x plus 2. Well, we have been talking about vertical stretches, okay, not horizontal stretch. So let's look at why this is a horizontal stretch. So if we start with just a quick graph, we have y here, we have x here. So this one is just right, it rises up 2, but it's just that standard graph of y equals x, but it's just shifted up 2. Okay, as soon as we do 0.2, then we have a slope of 1 to 5. So if we rise 1 here, then we run 1, 2, 3, 4, 5 for our second point. So this one's much flatter, like that. But just like a parabola, we just changed the reference point a bit. If we look at this like the x-axis, but it shifted up 2, so it just moved up 2, then we can see that indeed is a vertical compression toward this, but it's a horizontal stretch toward that axis because it's in reference to the x, which makes it in reference to this axis. So this is so the 0.2 is less than 1, and it's also greater than 0. So that's what makes it a vertical compression or a horizontal stretch. Okay, but because this isn't just affecting the whole, so when we look at it like this, g of x equals k f of x, this k is not affecting the whole function. So that makes it not necessarily a vertical reference point. But when we look at it as this, f of kx, though it is not affecting this, it is affecting this x. So to be a true horizontal reference, this one would also need to be multiplied by 0.2. So in this case, it could be either or because this should have been a slightly different number if we're going to multiply all of this function by that. Okay, so then we look at this one here. We want to write a function with a graph that is a horizontal compression of the graph of f of x towards the y-axis. Okay, so a horizontal compression. So that means we want our graph to move toward this. So our g of x, instead of having the coefficient out here, what we're going to do is we're going to put the coefficient in here. So we're doing a compression. So the compression then is going to be, we're going to think about it. Let's think about this. So if we have, this is our cube root, we want the horizontal compression, so we want it to be farther away. So that means we're going to do 7x in here. Okay, so for every x, so if I had 1 in here, or let's say 49 in here, 7 times 49, which is way out here, would be 7. Would that work? Okay, so let's take a look at that again. So let's use some Desmos really quickly and see, because sometimes this can be a little bit challenging. Let's go to Desmos. Oops, this is in the way. All right, so let's put this in here. F of x equals, now if you can't do the cube root, then what you can do is parentheses, and we could do x, and then we're going to do a little 1/3, which is a cube root. There we go. All right, so that's what we're dealing with. Now it says what we want to do is the horizontal compression of the graph of f of x toward the y-axis. So we want it up there. So what we're going to do is g of x equals, and let's just copy this really quickly. But I'm going to put a k right there, and we're going to add that k slider. All right, let's see what happens when it's a fraction. See the fraction, how it's stretching away from the y-axis. So that would be a horizontal stretch or vertical compression. Okay, we're trying to write a horizontal compression, which means it needs to move toward the y-axis. So if we move it to k is 7, as I've put down there, see how it's now closer to this y-axis. Okay, so let's take a look at the next problem. So if we're going to do this final one, g of x equals, we're going to put this in the same way. We'll put 6x squared here. Where this is a horizontal compression, it's moving away from the x-axis, and it's moving toward the y-axis. So let's put that in there. So we have x squared is our purple, but then down here we have parentheses kx in parentheses, and then we're squaring it. Look at that. That's a big stretch toward the vertical axis, a very tight stretch. So that's compressing very far away from the x-axis, but it's stretching vertically toward this y-axis. But because this k is inside the parentheses, that's what makes it relative to the x-axis and not the y-axis now. So that's what makes it a horizontal compression as opposed to a vertical compression. All right, well, that's it for today. Have a wonderful day. Bye-bye.